Let's get started on today's notes over an introduction to logarithms. So what is a logarithm? A logarithm, that's how you spell it, is the exponent to which a base is raised to obtain a power. So the log is the exponent. That's what I like to say. The log is the exponent. Okay, so we've just gone over exponentials, exponential properties of exponents, exponential graphs and patterns, and now we're moving to an introduction to logarithms because a logarithm is actually an inverse operation for an exponential expression or equation. So just like we use inverse operations to solve other types of equations like linear equations, right? We might, to undo addition, we use subtraction. To undo raising a base to an exponent, we will use a logarithm. So that's why we're moving on to logarithms after we've reviewed the properties of exponents. So the first thing that we're going to do when we're talking about logarithms is we're going to rewrite exponential and logarithmic equations. So you can write an exponential equation as a logarithmic equation and vice versa. So we're just going to practice rewriting these equations. If you look at this one over here, this is an exponential equation, and it's read as b to the power of x equals a, or b to the x power equals a. Over here, this logarithmic equation is read as log base b of a equals x. So as you can see, the b is the base in both equations. But one of the easy ways that I like to teach this is I kind of go just like clockwise. B, if I'm rewriting this exponential equation on the left, so b to the power of x equals a, b, or log base b of a equals x. So log base b of a equals x, and I kind of go around that way. I can rewrite the logarithmic equation in exponential form doing the same, right? B to the power of x equals a. So let's do that. In problems 1 through 6, we're going to rewrite each exponential equation in logarithmic form. So I'm going to do my kind of counterclockwise thing, and it's log base 3 of 81 equals 4. So I would write log base 3, that's that subscript, of 81 equals 4. And when I say the log is the exponent, look, log base 3 of 81, what is it? It's 4. That's the exponent right up here. Let's rewrite number 2. Log base 7 of 343 is 3. Log base 7 of 343 is 3, or equals 3. Same thing over here. Log base 4 of 2 is 1/2. Log base 4 of 2 equals 1/2. And I just want to remind you, and the only rational exponent that we're going to be working with today is an exponent that's 1/2. So what is this rational or fractional exponent? You might recall, and we'll learn it later in the year, we'll review it, but a rational exponent, it's the power over the root. So I can rewrite it as a radical, x to the power of 1. I can take the square root of x. So anything raised to the power of 1/2 is just the same thing as taking the square root of that term. So let's move on to number 4. Log base 12 of 1 equals 0. Log base 12 of 1 equals 0. So what does that tell me? Because anything raised to the power of 0 is 1. So if I have this big number, variable here, whatever, or not variable, but the number right here, if this right here is 1, I know the exponent is going to be 0. Any number raised to the power of 0 is going to be 1. Let's move on to number 5. Log base 8. Let's rewrite it. Log base 8 of what? 1 over 64 equals -2, right? And remember that exponent that is negative, it yields a very, very small number, right? So 8 to the power of 2 is 64. 8 to the power of -2 is 1 over 64. Let's move on to number 6. log base 5 of 625 equals x. So all we're doing is just rewriting. So let's move on to the next set of examples where we're going to be rewriting each logarithmic equation in exponential form. So we're going to be doing the same thing but in reverse, and I just go in the same order, right? My little counterclockwise thing. So on number 7, it's log base 4 of 64 equals 3. If I rewrite it, that's 4 to the power of 3 equals 64. You'll find in this unit, sometimes it's hard for your brain to like understand things, and if you just rewrite it in a different form or a little bit differently, it can make so much better sense, so much more sense. So let's read the next one, or let's do the next one. 8 to the power of 1 equals 8. 8 to the power of 1 equals 8. So what do we notice here? If I have a base right here is the same thing, it's going to be 1. And we'll learn that, we'll actually review that when we're going over the properties of logarithms. Let's move on to number 9. Let's log base 6 of 136 equals negative 2, which means 6 to the power of negative 2 is 1 over 36. Let's do the next one. What is that going to be? X to the power of 2 is 25. What about the next one? 16 to the power of negative 1 over 2 is 1/4. So let's kind of break this down, because some of you might go, what? 16 to the power of 1/2 is just the square root of 16. And what is the square root of 16? It's 4. So 16 to the power of negative 1/2 is going to be 1 over 4. Let's move on to number 12. 2 to the power of x equals 16. And some of you might be able to say, okay, 2 to the power of x equals 16. Well, what is that going to be? Well, x would be 4, right? 2 to the power of 4 is 16, which you're not asked to do that in these, but you can figure those out. So let's move on to the next set of examples, which are common logs and basic logarithmic equations, where we're going to be doing basically what I just did. So let me see if I can change colors here just because I want to. Let's do this. So a common logarithm, I'm going to write this down. A common logarithm is a log with a base of 10. If a logarithm does not have a base, that's that little subscript, the base is assumed to be 10. So let's say something is written like this, log of 100. Well, that's the same thing as log base 10 of 100. So there's assumed to be a base of 10 if nothing is written there, okay? Which means 10 to the power of what is 100? 10 to the power of 2. So the log of 100, what is that? It's 2, okay? And I can just simplify it just like that. So that's something to just note, that if there's not a base there, it's 10. So in problems 13 through 16, we're going to solve each basic equation involving logs. So on number 13, it says log base 5 of x equals 2. Well, that's the same thing as 5 squared equals x. So when we're solving this, we're solving for the variable. Well, what is x? It's 25, right? Because 5 squared is 25. Let's move on to number 4. Log of 100 equals x. Well, what's the base if nothing is written? It's 10, right? Base of a log is the same thing as your base in your exponential form. So if I rewrite it, 10 to the power of x equals 100. Well, what is x? X is 2, because 10 squared is 100. Let's move on to number 15. If I rewrite this in exponential form, 6 to the power of x is 1 over 6. What would x be? Negative 1. Let's move on to number 16. If I don't have a base there, it's assumed to be 10. You don't have to write it in, but if you need to visually see 10 and then rewrite it like this, that's fine. 10 to the power of 4 equals x. So what does x equal? X equals 10,000, right? Because 10 to the power of 4 is 10 times 10 times 10 times 10, and that's 4 zeros. That's 10,000. Let's move on to the properties of logarithms. The properties of logarithms are derived from the properties of exponents. So when you see these properties, you might kind of say, hey, that kind of looks like the product property of exponentials. But the product property of logarithms, the quotient property of logarithms, and so on and so forth, you just might see some similarities. So what I like to say is whenever we're going to use these to expand, condense, and solve logarithms, it helps to just rewrite the log in a different way. Okay, so that's what, and you're going to use the properties of logarithms to do this. So the product property, what does this state? This state the logarithm of a product, so whatever is in here, okay, if I break it out like into, if it's a number and I break it out into two numbers, that's that the main number is a product, the two numbers are factors. So the logarithm of a product is equal to the sum of the logs of its factors. So what I can say is the log base a of m times n is equal to the log base a of m plus the log base a of n. So let's look at number 17, this example over here. Log base 2 of 10. Well, I can rewrite this as the log base 2 of, give me two factors, 2 times 5, right? So this would be considered the product, and these would be considered the factors, right? So I can rewrite this as the log base 2 of 2 plus the log base 2 of the other factor, which is 5. So I'm just rewriting it. And that's what we're going to be practicing, is we're just going to be practicing rewriting these logarithms in a different way. Okay, moving on to the quotient property of logarithms. So the logarithm of a quotient is equal to the difference. So log base a of m divided by n is equal to the log base a of m minus the log base a of n. So moving on to number 18, log base 3 of 9 divided by 2. That's the same thing as I can rewrite it as the log base 3 of 9, right? That numerator, minus the log base 3 of 2. Moving on. And one thing I do want to say, and I want you to write it down, if there's a minus sign in front, okay, so if there's a minus sign in front, it goes in the denominator. And you'll see that. It goes in the denominator, okay? So if there's a minus sign in front right here, it'll go on bottom. So if I went the other direction from this expanded form and I condensed it to this up here, I would know log base 3 of, this goes in front, and then there's a minus sign right here, or not in front, on top, so this will go on bottom, okay? 9 over 2. And we'll practice that on the next lesson. So properties of logarithms continued. We have a couple more. The power property of logarithms. So if a logarithm of the logarithm of a power is equal to the product, meaning I multiply, of the exponent and the log of the base. So if I have an exponent right here, I can take that exponent and I can put it in front of the log, and basically I'm going to be multiplying that exponent times the log of all of those things. So this should be an m right here. So log base a of m to the power of n equals n times the log base a of m. So I take that exponent and I moved it in front, like right there. So on number 19, if I wanted to rewrite log base 4 of 16 cubed, if that has an exponent right here, I can move it out in front. That's the same thing as the product of the exponents, so 3 times log base 4 of 16, right? I'm just rewriting it, okay? And I actually know what log base 4 of 16 is. What is log base 4 of 16, right? What's the log of that? 4 to the power of what is 16? 2. So this would be like 3 times 2, and that would be 6. So I can simplify it that way when I use these properties. Moving on to the inverse properties of logarithms. So log base b of b to the power of x equals x, where b has to be greater than 0 and b can't be 1. So what this means is if the base and this right here are the same, it's going to be the exponent. Okay, so for example, on number 20, log base 8 of 8 squared. I have an 8 as a base and an 8 right here, which means my answer is 2. So the log base 8 of 8 squared, it's just going to be the exponent, right? So moving on, number 21, log base 4 of 64, where you're like, well, that's not the same. 4 and 64 are not the same, but I can rewrite it, all right, which is a big thing in this unit. You can always rewrite it. Think about these numbers differently. Can you rewrite 64 with a base of 4? You sure can. Log base 4 of 4 to the power of what? 3. So 64 is 4 to the power of 3. I can rewrite it with a base of 4, okay? Well, now I can use this inverse property where I have the same right here, and so my answer is just 3. Number 22, log base 4 of 4 to the power of 2x minus 1. Well, what am I left with? 2x minus 1. Number 23 looks a little different. It has the same property. 3 to the power of log base 3 of 8. I have the same base right here that I do right here. So I'm going to use this inverse property of logarithms. That's 1, and I'm left with 1 times 8, and I'm left with 8. Okay? Okay, moving on. The last two examples of today's lesson. I'm going to try to do these very quickly because I know this is a long lesson, but this is the last thing we're going to do today. So the following information is given. The log of 4 is approximately 0.602, right? I rounded to the three places after the decimal, the thousandth place. And the log of 5, is approximately 0.699. So this is information that you're given. We're going to use this given information and the properties of logarithms to find each logarithm. So on number 24, it says log of 20. Well, I only know this information that I'm given, and I could plug that into the calculator, log of 20, but we're not using a calculator right now. So I'm actually going to rewrite the log of 20 as the log of 4 times 5. Because 4 and 5 are factors of 20, and I know what the log of 4 is, and I know what the log of 5 is, because I was given that information. So now let's use our properties of logarithms to expand this. This is the log of 4 plus the log of 5. Can I use that product property of logarithms? I sure can, right? So it's equal to the sum of its factors. Well, I know what the log of 4 is. What is it? It's 0.602. And I know what the log of 5 is. It is 0.699. And now I can just add those together. So I've got 0.699 plus 0.602. And when I add these together, I get 1.301. So the log of 20 is approximately that. And if you were to plug it into your calculator, you could check and you would see that it is approximately 1.301, right? We've rounded it. So let's move on to our last example, number 25, the log of 64 over 5. And again, I don't have what the log of 64 is, right? I have what the log of 4 is, and I have what the log of 5 is. So can I rewrite 64 to have a base of 4? I sure can. I can rewrite this as the log of 4 cubed over 5. And now let's expand this using our properties of logarithms. So we've got a quotient here. So I know that I can take the log of 4 cubed and I can subtract the log of 5, right? We can subtract. But I'm not done. I can use that power property to do what with this exponent right here? I can move it in front and multiply it times the log of 4 minus the log of 5. So now we've got the log of 4, which we know to be 0.602. So that's 3 times 0.602 minus the log of 5, which is 0.699. And now we're just going to use our order of operations to simplify this. I've got 0.602, and I'm going to multiply that by 3. 3 times 2 is 6. 3 times 0 is 0. 3 times 6 is 18, and my decimal is going to go right there. 1.806 minus 0.699. So now I'm going to subtract. Make sure you line up your decimals. 0.699. And so we're doing it old school. We've got to do this by hand. I can't do 6 minus 9. I got to go over here. Change that to 7. That becomes 10. Change it to 9. 16 minus 9 is 7. 9 minus 9 is 0. 7 minus 6 is 1. Bring down my decimal, and I've got 1. And my answer is approximately 1.107. And that concludes your very long notes over day 1 for your introduction to logarithms. I hope it was helpful in helping you understand this very new concept and what everything means. So good luck.